Welcome to the donut shop. What would you like today?
What's today's special?
Today's special are charged donuts.
Whoa, what are those lines coming out of it?
Those are its electric field lines. To understand electric donuts, let's first delve into the math behind rings of charges. So to understand the E fields around a full ring of charge, first take a small section of the ring, which has some small charge, let's call it dq. The point charge feels a partial electric field from that specific segment of the ring. Let's call that some partial E field, dE. If we go directly across, we'll see that another dq, towards which the dE is pointing, produces a dE in the complete opposite direction. Now, this is true for anywhere on the ring, and you'll notice that all of these vectors are equal in magnitude and pointing opposite in direction. And since they're equal in magnitude, they cancel each other out. That means right in the center of the ring, the magnitude of the E field equals 0. But what if we only have half the ring? This time, we can once again draw our dq, and it produces a dE directly on the point charge. We can break our dE into two components, the horizontal and the vertical components labeled as dE sub x and dE sub y. Let's arrange them as so we can better see their magnitude. And we can draw another dE in this direction, and it can also be broken down into its components. If we arrange the components as so, you'll notice that the vertical components are equal in magnitude and opposite in direction. Therefore, they will cancel out. However, the x contributions point in the same direction, and therefore they amplify in magnitude. And this is true for anywhere on the ring. Therefore, if all of the partial charges are added up, there will only be a force felt in the complete opposite direction as the ring, and the sum of all the partial dE's in the x direction add up to produce the total E field felt in that part of the ring. However, let's derive some equations to better understand what the E field really looks like. Let's label the radius of our ring as capital R, and let's call the angle at which our dq is as phi. If we draw a dE coming in the opposite direction, we can once again break that into its vertical and horizontal contributions. And you'll notice that these are alternate angles. They will be the same. Now we can derive specific equations for the x and y contributions on their own. To do so, we can look at their relationship to phi. Since dx is on the opposite side, we can say that dx equals dE sine phi and dEy equals dE cosine phi. So, to derive any E field equation, we look at Coulomb's law, which says E equals kq over r squared. Since we're only looking at an infinitesimally small contribution from the E field, we can convert our q into an infinitesimally small contribution of the charge. So, we can rewrite our equation as dE equals k times dq over r squared. Let's bring in our definition for our dEx contribution and substitute Coulomb's law into it. Now, our next task is to replace all these variables with variables that we know from our diagram. Let's take a closer look at what dq can equal. We can go about it two ways. The first one is using proportional density. We can say that for every fraction of charge per total charge, there is a fraction of angle per total angle that our ring covers. Rearranging this, we get that dq equals q over phi d phi. Pretty straightforward. The second method we can use is by using charge density. So we can say that lambda, which is the linear charge density, is some small charge over some length dy, since our ring is sweeping on the y-axis. We can rearrange that to say dq equals lambda times dy. Now, if we bring in another definition, circumference of a circle equals 2 pi r. And that is true for a full circle. What if we only have half a circle? Divided by 2, pi r. Or, in more general terms, y equals phi r, phi being in radians the angle swept by a ring. And if you take the derivative of y with respect to phi, we get dy d phi equals r, or dy equals r d phi. Now we can combine dq equals lambda dy and dy equals r d phi to say that dq equals lambda r d phi, or q over phi d phi. As you can see, the last definition that we got is the same as the one we got using our first method of proportionality. But while that method was easier to do, it introduces a factor of 1 over phi, which would be harder to integrate since we already have a sine phi. So we're going to use the first definition, lambda r d phi, for now. Now let's sub in our definition for dq. Little r is just the distance of dq from our point charge, which is consistent throughout the ring as big R, so we can substitute big R in for r squared. And one of the factors of the big r's cancels out with the bottom, and we only have k lambda over r sine phi d phi. Now we can integrate both sides to get e sub x equals integral of k lambda over r times sine phi d phi. We can pull out our constants, k lambda and r, since those values are not changing, and integrate the rest. Before we can integrate, we need to know our bounds. Our bounds are from our initial angle, phi, all the way to our total angle that our ring sweeps through. Solving this integral, as such, gives us a negative k lambda over r times cosine phi minus cosine phi initial. Since we have a negative, we can distribute that into our cosine difference and switch those around. Now, we can just sub in a 0 for phi initial, assuming that any angle can be written as 0 to some angle in radians. So cosine of 0 minus cosine phi. Doing that, we get 1 minus cosine phi as our factor. We can also sub in the definition for lambda. Lambda is just charge over length, which is a total charge q over the circumference that we discussed earlier, phi over r. Subbing that in, we get kq over r squared. And we can group our phi terms together to get an equation that reads kq over r squared times 1 minus cosine phi all over phi. Great, now we can do the same thing for the y contribution. We follow the same steps. We can still use the definition for dq that we derived earlier and substitute that in, and we can still substitute in a big R for a little r and cancel the terms out. The integral works the same way, but instead of having an integral of sine d phi, now we have an integral of cosine phi d phi. Notice we do not get a negative factor this time anymore, as the derivative of sine is positive cosine. So we do not need to switch these anymore, but our bounds remain the same, initial phi to final phi. And once again, we assume that it starts at 0 and goes through some angle phi. So we can substitute 0 in for initial and get sine of 0, which is 0, so that term just goes away. Once again, let's substitute in our definition for lambda as q over phi r, and simplify to get kq over r squared times sine phi over phi. One thing to notice is that we pretty much rederived Coulomb's law times some factor using phi and some trig functions. Now let's take a look at the Efield felt by a point charge that is some height z above our flat ring sitting on a table. Once again, we can look at symmetries to see if there are any contributions that are of significance. If we plot a dq in this corner, it generates a dE component going in that direction. Similarly to the 2D ring of charge, we can break this into components, one that is parallel to the z-axis, and one that is perpendicular to the z-axis. Now, the perpendicular one can further be broken down into its x and y components, but for now, let's just think about it as the perpendicular one. Now, let's plot a dq on the complete opposite side, which is where the dE is pointing, if we recall the symmetry from the first part. We once again get a contribution going in the opposite direction, and once we break that down, we'll see that the perpendicular components from both of these dE's opposite in direction and equal in magnitude. Therefore, they cancel each other out, whereas the dE parallel contributions are in the same direction, so they amplify. And once again, for any of the points on this ring, we get a charge that is parallel to the z-axis. This means for this scenario, the x and y components both cancel out, and the only component left is the z component. We can once again break this down into a half ring of charge so that we can actually derive the equations to help us understand all of these scenarios. Let's once again label our diagrams. Capital R to represent the radius of our ring, and phi to represent the angle through which our ring sweeps. Now, if we take a dq over here in this corner and we draw a directly opposite dE contribution, we see that the angle between them is not the same as our phi anymore, so let's call this one theta. You'll notice that the contribution that is parallel to the z-axis can be written as dE cosine theta, and the perpendicular one can be called dE sine theta. Now let's further break down our dE perpendicular component by looking at a graph from this angle. This looks identical to our graph in our half ring of charge equation, but the only difference is that instead of the x and y components having dE cosine phi or dE sine phi. We now have dE sine theta sine phi or dE sine theta cosine phi. So we can once again write them in the exact same way as we did earlier. And just sub in our sine theta next to both. Perfect. One more thing we can do here is that we can define what sine theta equals. If we look right here, we have a triangle. So we can actually define what sine theta equals. The opposite side is a capital R, and the adjacent side is the distance z, the height z that we're above our ring. By using Pythagorean theorem, we can say that little r squared equals big R squared plus z squared. And we can say that our little r, which is our distance from our charge to our point charge, just equals the square root of big R squared plus z squared. What does sine theta equal if you look at this triangle? It is opposite over hypotenuse, which would be r over the square root of r squared plus z squared. And while we're at it, we can also say that cosine theta equals z over the square root of r squared over z squared. These can be plugged into our equations later. You'll notice there's a big R right here, but we can no longer use our big R, so we'll have to replace that with our little r. And as we just defined right now, little r equals the square root of big R squared plus z squared. Now let's go back to our z contribution, which was, as we wrote earlier, dE parallel. So once again, for the parallel component, we'll pull out Coulomb's law and sub in our definition for dq equaling r times lambda times d phi, with our little r being the square root of r squared plus z squared. When we substitute that in, we get k times lambda times r times z all over r squared plus z squared to the 3/2 d phi. Since there is no sine phi or cosine phi here, everything else is a constant that can be pulled out. And the integral ranges from phi initial to phi final once again, which we can also call 0 to phi. And the integral of that is simply phi. Like we did earlier, we can sub in our definition for lambda as q over the circumference, which is q over phi r. And once again, we can pull aside our factors. And here are the final values for all three of our components. Now, if you further think about these equations, there are three variables really that we can alter to change the magnitude of our Efield. The first is the length of our ring, which we defined by using phi. If it was a full ring, phi equals 2 pi, half a ring, phi equals pi, etc. The other variable we can change is big R, which is basically the radius of our ring. We can make it as big as infinity, in which it would just be a ring surrounding everything, or as small as 0, at which point it's just a point charge, really. Next thing we can change is z, which is the height at which our point sits. Here we have a graph that shows the magnitude of the E field for each of these z values as we change the phi at which these rings sweep. On the left side, we have a graph that is plotting that on a 2D plane and just shows the magnitude as a graph. And on the right, we have an actual ring demonstration of what that would look like. As for varying the radius, we can look at Coulomb's law and determine that the radius of the ring follows an inverse square law. So as the radius increases, the field decreases by a squared amount. So in this graph, we'll only look at varying the length of the ring and the height at which the point charge lives. As you can see, for the x component, the magnitude increases in the direction opposite to the ring at all times. When we have just half a ring, our magnitude goes to 0, and then it goes to maximum in the opposite direction. For our y component, our full ring once again starts off at 0, as we would expect, and as we open the ring a bit more, it goes to its maximum when the ring is half, and then goes back to 0. The z component is a bit different. It starts off at having maximum values at both the top and bottom. On the left graph, it looks like negative and positive, but that is simply because of the height z is negative or positive, if we think of vectorized values. But magnitude-wise, it's the same. As we decrease the length of the ring, we're really just decreasing the amount of charge that's on there as well, so the magnitude also decreases. Here is a comparison of the x and y graphs together. As you can see, they're not in phase. They're 90 degrees out of phase. While one hits its maximum, then 0, then back to its maximum, the other one goes to its maximum on the half ring and then goes back down to 0. But what if we want to look at the E field generated for the whole ring rather than only looking at x, y, and z components? We can do so by using Pythagorean theorem. We can simply add the square of each of our contributions to get our final E field. If we just add our x and y components, here is the graph that is generated by it. It goes to its maximum and then slowly dies out. But if we combine all three of them, the graph produced looks as such. This time, it shows the positive values. And as you can see, when there's a full ring of charge, there is no charge in the middle, represented by the 0. But as you move to a certain height, there's a maximum, after which it starts flattening out again. However, as you open the ring, all of a sudden the center starts experiencing a lot more charge, after which it becomes the maximum point of charge. And once again, it sweeps in the opposite direction of where the ring is and slowly comes to a close.